So this is the part 2 of the different geostatistical analytical methods in graphite resource estimation. In part 1, as you have seen, we have discussed about variography, then kriging, and in this part, remaining two major process we'll discuss. First one is IDW, inverse distance weighting, and another one is simulation, different type of simulation is very much important also in for that machine learning is very much essential. Let us start with IDW. It is a simple and widely used method for spatial interpolation, particularly in resource estimation in mining. The principle behind IDW is that the estimated value at a point is more influenced by nearby sample points than those further away, using the idea that things that are closer are more similar. Definitely. So it is everywhere truth and applicable in case of spatial statistics. Let us have an example so that it can be easily understood. For example, if we have four drill holes A, B, C, D, and their location is there. From origin, a reference, let us fix 0, 0. From there, along x means maybe east west, direct east, and y means north, suppose. Okay, so these are the coordinates, and these are the known graphite grade. These are the drill hole location. Okay, so if we plot this, this is east, this is north. So east is x-axis, north is y-axis. So this A, B, C, D, these points as I have also shown here. See, this is 10, 20. Along east it is 10 from 0, 0, and along north it is 20. Likewise, all the plots, if we see, these are the known points. Now we'll show how to calculate IDW. This is one single example. In this way, entire area should be covered. For that, software will do, but principle behind that must be understood. That is why I am showing one single example. Okay, so to understand and to calculate the possibility and probability of most likelihood of getting graphite grade at unknown point P. For that, we, for example, if we see P location is coordinates 0.25, 35. Okay. So in this point P, what will be the grade of graphite? By using IDW, it is possible to estimate. So direct distance from all known points must be calculated first. So from A to P, from B to P, from C to P, from D to P. These distance are easily calculatable like this, root over of x2 minus x1. x2, for example, this known points. Okay. So along x, along y, you have to likewise you can calculate the distance of unknown point from all known points and then apply IDW formula. This is the IDW formula where Zi is grade of samples at different points, like here 5% EGC, there in B 6% EGC. Okay, and Di is distance from point P to the sample points, as I have shown this distance. I'll show everything. And here Di to the power P, P is power parameter. In general it is used 2, power is 2 means square. For example, distance, by using that formula, distance of point P from A, just coordinate, from coordinate you can calculate. This is 21.21 meter. Similarly from B, it is, you see, from B it is nearby 7 meter. From C 35, from D 63 meter. Okay, 63.64 to be more precise. So in this way, after calculating all the distances, you can easily calculate that Z value by using that formula as I have shown in the step 2. So in step 1 you will have to first determine the distances, and then step B, apply IDW formula. Here this is the IDW formula Z. So if we calculate this, how much it is coming, you can easily see. This is coming how much? This is coming around 5.95%. Okay, here 5.95. All numerator you sum up and denominator sum up, then divide. So in this way, by using IDW, we can easily estimate the grade at unknown points based on known points surrounding this unknown point. See, here it is 5%, here it is 6%. So since P is situated very closer to point B, so weightage will be given more. Weightage of B will be given more to P. So it is 5.95, which is very closer to 6%. Whereas since it is away from point A, which is having 5% TGC, so it is from A to B, if you see, 1% TGC enhanced. So in between distance A and B, P is situated, but P is situated nearby B. So its value, TGC value will be more closer to that in B. Okay, and here, by the way, weightage from C, weightage from D also is given. So all the surrounding points are equally important, and therefore likelihood of getting error is very much limited. Most of the times IDW give fair enough data. Then simulation method. Simulation is there are two types of simulation: sequential Gaussian simulation SIG and SIS, sequential indicator simulation. For this, sophisticated instrumentation very much essential, especially I think machine learning and software. This knowledge is very much essential, because this is very difficult to calculate manually, because for spatial statistics so many data are generated, infinite number of points may be present. So here is a comparison between SGS SIS, between SGS and SIS. And as far as data type is concerned, for SGS, from the term itself you can understand it must be normally distributed. Gaussian distribution is essential. Whereas for SIS, continuous or categorical, not necessarily it is required to make Gaussian. Okay. Then output is realizations that reproduce a Gaussian model. Whereas in case of sequential indicator simulation, output realizations that respect indicator threshold. And handling non-Gaussian data, if we see, only SIS can handle non-Gaussian data. And compared to SIS, SGS is relatively simpler, fewer transformations, but SIS is very much complicated and handles multiple indicators. But endpoint, if we see, SIS will give further more detailed things. So if we want to summarize, there are few key points which we can remember for time being. SGS is more suitable when data is transformed into Gaussian distribution or data is already Gaussian distributed, while SIS is better for categorical data or non-Gaussian continuous variables. Both methods generate multiple realizations, multiple probability, providing insights into spatial uncertainty and variability. From that, you will have to choose most realistic output. SGS and SIS are widely used in various industries including mining, exploration, environmental studies and hydrogeology, and it is most often give successful estimation. Whenever it is getting validated, it is observed that that simulation gives very much realistic, closer to realistic estimates. Main purpose of SGS is used to create multiple equally probable realizations of a spatial variable that follows normal distribution. The goal is to reproduce the spatial variability histogram, semi-variogram of the variable being simulated. So far, we have talked about simulation and simulation. In brief, I can say simulation is a technique used to model or imitate the behavior, process, or characteristics of a real-world system, phenomena, or process. In essence, simulation involves creating a virtual model that represents key elements and dynamics of the system being studied, which allows us to analyze how it behaves under different scenarios or conditions. Here are a few steps to perform SGS. First, you must understand these 7 stages. Okay, first transform data to a normal distribution, then establish a random path, then kriging estimation, then draw a random value, then update the data set, repeat until all nodes are simulated, and then back transform the data. No, don't worry, this is not at all a user friendly process. For that, always machine is required. Machine learning is essential. Software related things, it is very much complicated, so I will not go into detail, because without having software you cannot imagine. It is relatively is difficult to grip, but you must have a basic idea. Okay, so machine learning is significant in this context. Simulation methods require specialized software and machine learning techniques to effectively model spatial variability, uncertainty, and resource saturation. For example, this is a space, maybe some area where few, as much as possible, sampling is being done. Okay, these are the sampling points. Or you can imagine borehole data. From borehole data, sampling has been carried out, and those samples are given different values of graphite TGC content. So extremely blue color is lower value, extremely yellow color is higher value. So these are the points where from data is available. Now these are the point data. We need to understand the total space, how it is distributed. For this, you can imagine now, only manual statistics is you cannot calculate it by hand. Okay, software is essential. Now using, so in the principle behind software must be understood. Those principles, as I have told, these are the steps. Software will be generating different realistic situations. From there you will have to choose which one will be most suitable. For example, there is 2 realizations produced by SGS. See, this is the zone where graphite can be expected to be high. Okay, and this print graphite is relatively lesser. Okay, so minor variation will be there, but for accurate estimation, definitely end product will be one of them. So it is essential to understand what are the prerequisites, what are the main requirements to perform such statistical analysis, especially simulation. For I have prepared two comparative study for SGS and SIS. Firstly, if we see the software requirements, SGS is mainly performed with GSLIB, SGEMS, iStats, NeoSurfer. Here, same software can be used for SIS as well. Now, programming languages, if we see, there is also not having much differences. Machine learning techniques, variogram modeling, deep digging. But here, in case of SIS, indicator regression is essential. Okay, this is the difference. Main machine learning techniques must be understood here. Then ML libraries, these are the almost same. Hardware requirements almost same. And as I have told, GPU if needed. These are the details. So to outline the key software options, libraries and machine learning requirements commonly used for implementing these geostatistical simulation methods, you can understand now what are the basic difference. In brief, okay, when you will perform these things, then only you will understand much better and you will learn. By theoretical studies or such lectures, it is not possible to grasp until and unless you do it by your own. So this is the end of this video. Thank you. I hope I have successfully given a brief idea about the all statistical requirements for resource calculation.